I didn't have the best explanation for this one, guys, so... Uh-oh. Okay. So, we can just work on this. So, this is a problem set 7, number 2. A, I think. This is 2A. This was just the second part of the question. It's not 2B. So this is 2A. How much force does an 80-kilogram astronaut exert on his chair while at rest on his launch pad? So we have the definition of force is equal to mass times acceleration. And then we know his mass is 80 kilograms. His acceleration is 9.81 because of gravity, right? Gravity is only force acting upon him. In this free body diagram you see, this is a force due to gravity. So this right here would really be Fg is equal to m of the astronaut, mass of the astronaut, times the acceleration due to gravity, right? So we'd have 80 kilograms times 9.81 meters per second squared, and we would get an answer of 780 newtons. And for the B part, or the second part of the question, you would take, we were trying to find the forces acting upon him. So there's a force that's thrusting him upward, so he's accelerating up. So the direction of this force is up, right? Something's pulling him. So we have the sum of forces in in y is equal to mass times acceleration. We can take this definition. So we have force. We have the force that's pulling him up. Then we have this force that's pulling him down, which is obviously mass times gravity. And this should be equal to mass times the acceleration. And this acceleration that we're given here is 10 meters per second squared, right? So, first of all, in order to, we want to solve for F, we want to see what the force is that he exerts on his chair while accelerating at 10 meters per second squared. So, we would set them equal to each other, and we would add mg. So, in all reality, we'd have the force is equal to mg plus ma. To make this a little nicer, we can factor out. So we have F, or force, is equal to mass times g plus a. Gravity is 9.81. The acceleration we were given was 10 meters per second squared. And then this is times his mass, which is 80 kilograms. I think this is 80 times 20. I think it's something like 1600 newtons, right? You guys can correct me if I'm wrong, but this should be your answer. So how we started it is we took a free body diagram. We accounted for all the forces that were there. So we had the force, right, that was pulling him up, minus mass times gravity. And we could really label this F as normal, because normal is the force that pulls up, right? So we would have this force is equal to, this force, and then minus mg, because mg is in down direction, right? And this should be equal to mass times acceleration. Add mg to both sides. Get this factor, do it, and you got your answer here. All right, guys, thank you. All right, guys, so we have the next problem here. Double check I'm recording. All right, so we have a 55 kilogram sprinter exerts force F on the ground for 0.25 seconds and accelerates from 0 to 2 meters per second. What is the magnitude of the friction force? So we can solve this. Obviously, first we're given mass, which is 55 kilograms. I could do this two ways. There's a graph way to do this. I'll show you the graph way, and then I'll show you like rate of change way. So I guess so. So if we draw a graph here, we have forgive me. If I draw a graph here, we have a velocity graph. We have velocity versus time graph, velocity in the x, right? So we can label this as 2, and this is 0.25. We can get the rate of change, and this will give us the acceleration, right? So you would do, in order to find the slope of this line, which is taking the derivative mathematically, you would do y2 minus y1, y2 minus y1 over x2 minus x1. So y2 is 2, y1 is 0. Oh, this is a minus sign in the middle, forgive me. Let me erase erase that little thing. That was a blunder. All right, so we have 2 minus 0. And then x2 is 0.25. x1 is 0. So we have 2 divided by 0.25, which is equal to 2 divided by 1/4, which is 8, right? So we have 8. The slope of this line is 8. So that means when we take the derivative of this whole function, we get the acceleration as 8, right, for 0.25 seconds. So the acceleration time graph looks something like this. 2.5, and this is 8 right here. Acceleration just looks like this. It's constant, right? So in order to find the force using this method, you would just multiply by her weight, because this is the acceleration graph, and you know acceleration is equal to force divided by, that was a blunder. Sorry. We know that force is equal to mass times acceleration, right? So we already have the acceleration graph. So if we multiply by mass, we would get the force graph, right? So we would just multiply by 55 kilograms, and this would give us the force. So 8 times 55 is 440. So we know the force that she had to produce is equal to 400. The force she had to produce in order to go from 0 to 2.0 meters per second in 0.25 seconds is 440 newtons. And we know that mu Sn is going to be equal to the force that is outputted, right? So like, let's say an object is static on the ground, right? Let's use this for example. This, oopsies. Damn. So, let's use a better example. It's just her foot, right? We'll actually use a foot. Well, that does not look like a shoe. So, as the foot is moving this way, right? The foot is going to want to move backwards in order to push the person forward, right? So, this is the force due to the foot, right? And in order to run, your feet need to stay in contact with the ground, right? If your feet aren't in contact in the ground, it's like running on ice. So in order for this to happen, the friction force, or more specifically, the force due to static friction, has to be equal to the force that the foot exerted on the ground in order to keep it in the same place. So we know that this is our answer, and this is equal to mu Sn, and that's obviously equal to, not obviously, sorry, let me not say that, but mu Sn is equal to the force due to static friction, right? And this is the magnitude, 440 newtons. I could break this up into, it's like algebraic. If you guys don't really like playing around with graphs, you could do it like this. I saw Joel do this method. I wasn't thinking about it like this, but this is pretty good. So we can use a definition that A is delta V over delta T. Oh, this is the same definition I used, just minus a graph, because I did do this. Delta V is defined as VF minus VI minus TF minus TI. No, over TF minus TI, and this is equal to 2 minus 0 over 0.25 minus 0, and this is equal to 8. And then you would just take that, this is the meters per second, right? Squared, because that's acceleration. So you would multiply this by mass, which is 55 kilograms, and you would get 400. The force to the foot is equal to 440 newtons. And then you guys can just use the same process to prove why the force of the foot is equal to the force due to static friction. Alrighty. Okay, where's my mouse? Oh. Alright. Alright guys, I'm going to be doing problem set 7, number 9. I'll speak up a little bit more in this recording because the other ones might be a little bit quiet. I'm sorry if your ears get hurt by this, but it must be done. 7.29, please be a fun one. Nice. So this was a pretty cool one. So we have this figure here, right? By the way, this is force F. So we have block A, we have rope 1, we have block B, and we have rope 2. The mass of the rope is equal to 250 grams, this converts to, you move the decimal over 1, 2, 3 times, and you get 0.25 kilograms, right? And the mass of the boxes, and they're both the same, by the way, the mass of the boxes is 1 kilogram each. So part A is asking us, what is the force that is pulling this box, pulling this contraption up? If it's accelerating at 3 meters per second squared, what is force F? So we can use a definition. Force is equal to mass times acceleration, right? So in order to find the mass for this system, we have to add up all of these things, right, that are below this point right here. So, and our acceleration we know is given by 3.0 meters per second in the up direction, right? So first, let's calculate the mass, okay? So we have 2 ropes here and 2 boxes. So this would be 0.5 and this would be 2. So we have the mass of the system is equal to 2.5 kilograms. And the acceleration, we have to do a sum of forces, right? So your sum of forces in the y is equal to mass times acceleration, right? So our acceleration is this 3.0. So we would do the force F, right? We do minus mg, because mass times gravity is pulling this thing down, right? So this is our force that's pulling it up. And then the next force that's pulling it down is mass times gravity. All right, you see that? And then this, all of this is equal to mass times acceleration, right? So in order to solve for F, we need to move mg to the other side. And we get simply ma plus mg is equal to F. So we could factor. You can do it with factoring or not factoring. It just makes it a little more simpler, less numbers to plug in, right? So you get your force is equal to mass times acceleration plus gravity, right? So we know our acceleration was 3.0 meters per second squared, and our gravity constant is 9.8 meters per second squared. And you take this number, you multiply it by the mass of the whole system, which is 2.5 kilos. And you should get an answer of 32 newtons. This is for the A part. So in order to solve for the next part, we need to keep the same acceleration. So let me put this force, let me put the acceleration of the whole system is equal to 12.8, right? 12.8 meters per second. Because that acceleration is going to be same throughout the whole system. So this is the acceleration component of this force, right? So the next part asks for what is the tension at the top of rope 1? So the tension at the top of rope 1 has to apply for everything below rope 1, correct? So we would add this 0.25, 0.25 and 1, which is 1.5, right? So we'd get another one of these. So we can just do mass times acceleration. We can do 1.5 times 12.8. And by all means, if you guys wanted to do the same thing over and over again for the first step, you could, and you would get the right answer. This is just shorthand. We know this acceleration is going to be the same, right? This is meters per second squared. This is kilograms. You multiply this and you get 19 newtons. So this is for the second part. So we had 32 newtons first, right? For the A part. Whoa, my pencil is throwing a fit. For the B part, we have 19 newtons. For the C part, this is going to be just going down the chain. So we have, what is the tension at the bottom of rope 1? So this accounts for everything below rope 1, below the bottom of rope 1, of course. So it would be, oh, am I recording? Oh my gosh. I get scared every time, bro. All right, so you add this 1 kilo and you add this rope. So it's 1.25, right? That makes sense. So we do 1.25 kilograms times your acceleration, which we know is 12.8 meters per second squared, you would get an answer of 16 newtons. Hello? We could do that, yeah. I'm just filming a video for my psychology for my physics. Alright, sounds good. Alright, bye. Okay, so our last one, it says, what is the tension at the top end of rope 2? So all that rope 2 is carrying is the weight of itself, which is 0.25 kilograms. Multiply that by acceleration, which is 12.8 meters per second squared, and you get an answer of 3.2 newtons. And that is number 9. Perfect, guys. I hope I'm explaining good.